it's often you have some design guidelines, how is a headlamp working, how should it be look like, that it's feasible, that it works. So this is what I'd like to show in this talk. So here's again the first slide. Very short overview. So we at ZEUS make MLAs, micro lens arrays, but there are more micro optics. I will just introduce some different micro optics which are on the field, in the automotive field. What's the status, what's the trends, what's the situation, how it will look in the future. Then I will go to the micro lens arrays in the second step, since we are producing micro lens arrays. I will show the applications that are on the market currently and the advantages. In the next step, we'll focus on production, limitations, possibilities of productions. And then at the last point, there's a single module for a headlamp application to tackle the design rules and also go to efficiency, since this is a topic which is more and more discussed. So what you see here is different micro optics. So on the top left, there's this DRL from BMW, which has like very small micro prisms on there to shape the light in the way they want to have it. So this is already micro optics. This is not MLAs, but this is micro optics. You see the light carpet over there. This is the first product of micro lens arrays that was on the market from our company. Then there's another application which is the rear light from Ella. There's diffractive structures to enhance the efficiency, and then of course micro-optical headlights, where I will focus more also in this talk as another application of MLAs. But what you can see is that micro-optics are getting more important. It is used in different fields. It's used for different applications. It's used to hide the lighting function, so you have a design, and then with micro-optics on it, you apply the lighting function. So there is a lot of possibilities to use micro-optics for. So here is the trends, the patterns and trends. In 2000, sorry, so wrong button. So in 2010 we had like 5 patents in this area. So this is the number of applications. This is the year 2010 to 2021. This is headlights with microstructures. So this is not only MLA technology, micro lens array. This is microstructures. It can be diffractive structures. It can be micro mirror devices. But what you see clearly here is that the trend is quite clear over the last years, and I think it will go on. This is 2019, like everything you can explain it. It's COVID probably. But the trend is still clear, and I think it will go on like this. On the other side, we've seen it already before. The major trends in automotive lighting. You see this slim design, the lines which are going in a horizontal direction, but also going downwards in vertical direction. So this is from the BBN report, all the pictures, and the sim lighting is a big topic. But what we also see is that we have some kind of surfaces, so you don't see any lenses, probably they are hidden somewhere. But this is another trend, that you have a surface, an illuminated surface, most time for DRL, but in the future, a more surface-like appearance could be interesting for headlamps. So now I come to the micro lens arrays. This is the parts that we are manufacturing. Different application, light carpet as I've shown before, very small system situated here, projection on the ground. The first micro-optical headlamp, the Lucid Air, and the second micro-optical headlamp on the market is the Genesis G90. For those that are not that common with the micro-optical system, usually we have an LED and collimation optics, and this is the part of the manufacturer. So there's a lot of micro lenses. So in this case, this is roughly 1 centimeter by 1 centimeter, the overall chip. And the single lens is 0.8 millimeters. That's the dimensions where most of the micro-optical products are located with these dimensions. They can be different, they can be varied. I will come to this later when I have the production slides. So what are the advantages of using MLA's micro-optical systems? we see here different advantages. The first two, they are connected. So if you have a macro optical system and make it smaller and smaller and smaller, then there's somewhere a point where the efficiency goes down. And when the efficiency goes down, it's probably not the best thing for a headlamp. So what you can do, you make very small lens and arrange them in an array, and then you can make a very small system which has still the same efficiency like a big macro optical lens. So this is the advantage. So the efficiency and the slim design first are connected. Then there's more functionality because we have several hundred lenses in headlamps, up to 1,000 lenses. This gives different advantages. One advantage is that each lens is illuminating the full field, and so the overlay is giving a very precise and homogeneous appearance because it's from different lenses and it's not just one. And also for each lens there can be a slightly different design, slightly different grayscale. So a lot of different possibilities to shape the light in different ways you'd like to have. And then last point, which is I think very interesting, is the freedom of the design, because you have like the lighting function integrated in a single channel, and then you have the smallest module size, and this is what you can like align in a horizontal line or a vertical line, like I've shown before, or a more surface-like appearance. So now I come to the manufacturing process. You see it already here. So here's the end product, and this is where it starts on a wafer, and it's getting diced here. So usually what we have is, what we start with is a substrate which is made of glass, can be porphyrin or something comparable, but it's open to discussion what material is used there. Then the second step, there's a chromium coating applied, and this coating is getting structured with feature sizes. It can go to a few micrometers with the features. And on the other side, there's then applied the polymer, and on this polymer there's a stamp going down, forming the micro lenses, and then it's flipped around, and then on the other side there will be also some micro lenses also with the stamp. And you can use these tools to make different designs. So this is the light carpet design that we usually have. We have the lens array, the chromium layer, then the substrate, and on the other side the projection lenses. But you can also have different examples here. For example, wafer stacking. So you don't need to have the chromium layer on this side. It can be buried in the middle. So this is more a headlight system. I will come to this later why this is used for headlights, and this is more for light carpets. And also you don't need to have like the same lenses on both sides. You can have different lenses. You can have more freeform lenses, biconic lenses, and so on. So having finished this, then the dicing process is coming. You can see here the wafer, which is around 200 millimeter at the moment. This is also what we're currently changing. And there's the LNAs on there, and then it's getting diced and separated, so we have the single chip after the dicing. And there, this is a design rule, I would say. If this substrate thickness is getting too thick, especially when you have wafer stacking for headlights, so when you're up to 6 millimeters here in this area, this is working quite good, so it's getting thicker and thicker. Then the dicing time is getting longer, it's getting more complex, and the cost is also increasing. So being below the 6 millimeters or even smaller would be beneficial for this technology. Next point is the size of the element. It's usually in work on those wafers, you have like several effects, and this is just an example. If you have like the same amount of defects on the left side and on the right side, but the difference is you have small dice and you have very big dice. So the thing is that you here you cannot have like everywhere this big dice everywhere on the wafer, so the overall number is getting down. But also if here's a small defect, you just throw away a small part of this wafer. If here's a small defect, you throw away a big part of the wafer. So this is getting more complex. We're working on different wafer design to tackle this issue. But this is always has to keep in mind that when the design is very long, it's getting more complex, and this also has an effect on the overall pricing. So as I wrote it down here, the size of the die, so around about 20 by 20 millimeters is something what we prefer, but of course with discussion and having this in mind, and for the roadmap with different wafer design, it's also possible to do others. So now I'm coming to an example for a headlight. Here we have the light carpet, what you've seen before. Typically, what you have for the headlamp is that you have the LED, the collimation optics, and then there is the MLA here, is substrate. I think you can see it quite good afterwards. And just concentrating, so we have like the spot module, which is making the high contrast here in the center, and then there is a spread module, which is making more the broad illuminance, which does not have the high contrast, which is here in the center. But I will concentrate on a single module for the spot module and show how it looks like within the design, how the efficiency is related to the design. For the design, there is different approaches. What is good is that the LEDs that are on the market, they're already very small, so half millimeter, square millimeter in surface delivers up to 585 lumens today. So these LED, there are two different approaches. One can take just one, a single LED. There's an angle space, the output, which is quite collimated, or one can take three LEDs, which is a lot of light which is inserted there. And here in the angle space, you see there's a divergence in one direction, which is a little bit bigger. So now what we see is that when using this stacked substrate, the LED is getting collimated from the collimation optics, and then you can see the rays, they are focused here in the area between the two wafers, and this is what I call a pre-shaped light field. So it's already, the intensity is already. I'm here. Oops. So the intensity is already pre-shaped, and with a mask, you then design the cutoff line, and there is some different ways, and I will show the single channel. So here's a single channel of the overall system. So you see the overall system. Here's a single channel. And here is some guidelines, what is possible, or what's the limits, or what's the size where this technology is working quite good. So the target is to find the perfect focus, the perfect distances here to make the highest efficiency of the system. And what I chose for this system is 1.9 millimeter, because there are standard sizes around 2 millimeters. And then you will have to polish them, and there's 1.9 millimeters for this system, and this is working quite good with dicing later on, because then I have a system which is roughly 4 millimeters, which is working quite good. The other thing what can you optimize is then the focal length, or the radius of curvature of the conic, what I have here, and also the base layer. And for the optical design, it's good to have a base layer which is between 30 and 150 microns, so 150 microns or 100 microns as a starting point is quite good. One can do variation on the wafer thickness, but then the imprint process is working best because the pressure aligned on the dies while doing the imprint can be regulated quite well. And together the overall system, the second base layer, so this should be up to 500 micrometers. When it's getting bigger, it's bigger to have a good results on the lens shape afterwards. So when the focal point is too short, when the system is designed in a way that the focal point is here from this side, the light comes in here, it's here. Here is the chromium aperture, then a lot of light goes to the neighboring channel, and when you have stray light, it goes, and this is what you don't want to have. So this is not a good solution when it's too long. So focal distance here is from this area to focus here. Then in the aperture, a lot of light is lost. Yeah, it's reflected or absorbed. That belongs to the kind of aperture you have. So the best compromise is something shortly after so this can be optimized for both directions, for the X and Y direction. Usually it's not the same, it's a bit different. And then when it's optimized, a lot of light is going through this aperture. There's a slight defocus, so there's a smoothing already integrated in each channel. And this is the first optimization, so the focal length can be optimized in a way. It should be somewhere here, so that a lot of light is going through each channel. And the second thing that can be optimized is an offset between the projection channel and the illumination channel. So, and doing all this, you can see here, there is the incoming light before the mask. This is at this point, and then there's light after the mask. And when I just purely look on efficiency, not on intensity and so on, there's for the spot module, the efficiencies, not for the whole system, just for before and after, goes up to 85%. This has to be optimized, and for the overall system I have a comparison of a single LED and 3 LEDs. So the single LED is not that broad, and I have an overall efficiency, so efficiency is here at the beginning, 100%. After the collimator, it's roughly 70%, and here after the MLA, with a very simple design cut-off line, it's around 47% with an intensity of 9 kilocandelas for a module size which is 11 by 11 in size, so you can add more, like 2 or 3 on the wafer. And here it's 3 LEDs, the divergence is a little bit higher in one dimension, so the efficiency is a little bit lower, but the overall luminance, the overall flux is a little bit more. And there's another advantage when you take 3 LEDs instead of 1, is that when you just turn on 1 LED on the side or in the center, you're able to shift the hotspot of the overall system. So it's like a digital bending light what you can introduce with this system. And this is an advantage you don't have when you just take 1 LED. So as the last point, I come to the next step what we have in production. We have new dicing technologies what we're introducing. So currently the dicing is always a rectangle or a square. With new dicing technologies, we're able to have free-form dicing with different shapes. If you want to have like illuminated surfaces, then you can have these shapes. Yeah? You have a surface, you define it, and you can have your lighting emitting area in this way. Another point, what you can see is that on the top right, there's the slanted edges. So this is also possible that you don't have to go in 90 degrees angle. There are slanted edges. Also, this is possible. And what I was saying at the beginning, that you get into some problems with the amount of elements when you have this 200 millimeters round wafer. We're also looking into 300 millimeter square, so you can see the amount of elements you can put, and also you can make it longer is increasing it. So here on the last slide, you can see that there's a new demand for slim beam lighting, or the demand for slim beam lighting is not that new, but there is a demand. Or you have illuminated surfaces, and in this area, micro optics can enable these design features. We'd like to have the designs in certain limits I was giving to you for wafer thickness, for base layer and sec, where we can have an optimized design. And of course, for the next generations, we will reduce the pricing with new dicing technologies and also with new wafer technologies. And this is the end of my talk.
you.